Hping3. If we want to discover network devices, whether they're local or remote, and they're not responding directly to ICMP ping requests, we can still verify that they exist using TCP and UDP options. Hping3 has those options and a boatload more. Let's begin. I'd like you to imagine that you and I are sitting at a couple of computers, and from a command prompt we type in ping www.cbtnuggets.com and we press enter. And what do we know based on this? Well, taking a look at the response, we know that DNS is working because we used the name CBT Nuggets and it gave us back an IP address. Well, that's great. However, we're not getting a response. Does that mean that that website is not up? And the answer is very likely no. It just means that ICMP is being filtered. What other tools can we use to validate that there really is a device sitting there? Well, we already have a couple in our tool set. We have the Nmap and Zenmap that will both do it. And I want to share with you another command line option that can do the same thing, and it is called Hping. Hping3, the current flavor, replaced the predecessor Hping2, and before that Hping. It does pings, but it can do it not just based on ICMP. You can actually do it based on SYN request and other flags in the TCP header. You can do ping requests with UDP, looking for an unreachable message coming back from that device to trick the destination device into responding back to indicate that it is sitting there. In addition to doing that host discovery to find out that devices are there and maybe what ports are open, it can also do fingerprinting, very much like some of the other tools that we've discussed. With fingerprinting, if we know the initial sequence numbers are predictable, we can map that over to a specific operating system or family of operating systems that behave in that way. It can also act as a sniffer, we can use it as a flooding attack tool, and we can even do covert channels and initiate file transfers using Hping. So we try to ping from a Windows box. We could also ping right here from a Kali or a backtrack distribution. Ping www.cbtnuggets.com. There's no response, and that is very likely because there's ICMP or ping requests specifically being filtered. So we're going to do a Control-C to stop the attempt of that. And now let's use Hping to go ahead and verify. So when I talk about Hping, I'm talking about Hping3, the current flavor of it that's in Backtrack and Kali. Now, how do we get help? Do you remember? How do we get help for commands if we need it? Now, if you're saying, Keith, I know we could use the man pages. And that's absolutely true. So type in man space, the name of the command we need help with or want information on, which is Hping3, press enter, and there's the man pages. So we can scroll up and scroll down through them. That's all the documentation. So we'll hit Q to quit that. How else could we get help with this command called Hping3? And you got it. Just type in Hping3 and with a -H, and that will give us the help. Now there are dozens and dozens of options and switches based on if we're going to do TCP based or ICMP based or UDP based, etc. So what we'll do is let's do a few examples together, and as we start using some of these switches and options, I'll describe what they are. And as we use this tool together, I'll introduce the switches and options that we're using. I also have, just for you, in the Nugget download area under Nugget Lab downloads, I've got all the commands I'm using in this Nugget, so you can go ahead and use them as a reference as well. So let's use Hping, and the syntax we're going to use is Hping3-S, and the -S is right here on the screen. In fact, let me get my pen out. So we're going to be using TCP. It's going to use a SYN request going to that server, and the port we're going to actually be sending it to is port 80. Now, even if it wasn't port 80, let's say it was another port, it's very likely we could get a response back saying, you know what, I'm sending a reset, I'm not listening on this port, and that would also indicate that the device is there. So the -S is for the TCP SYN request. That's the name of the site we're going to go see. That's the port number. And the -C2 represents, I only want to do this 2 times. So a count of 2. Otherwise, it would just go over and over and over again until we do a Control-C to stop the process. So let's press enter, and sure enough, we have a response from port 80. So we've just verified our connectivity over to www.cbtnuggets.com, at least on port 80. Now that means routing is working for the packets going back and forth, and if that was our goal, that's fantastic. We also happen to get, as a bonus, some timer information, which is another valuable tool in assessing if there's delay, for example. Maybe we have a voice over IP application or something else, and that could be used as an indicator of the delay to a specific site. Here's another example of how we can play with some of the ports involved. We'll do Hping-S, again for a TCP SYN request, We'll specify I'm going to use a local IP address on my private network for this one, 192.168.1.38, which is a device that does exist on my local network. And take a look at this option right here. We have this -P for port, and the ++50 says go ahead and start at port 50 as a destination port. And then the -C5 says go ahead and repeat it 5 times. So it should send out a request going to destination port 50, then 51, 52, 53, 54 for a total of 5 packets being sent. Now the interesting thing is that if we send a packet out to a server or a device and the destination port is port 50, if that device replies back to us, the source port is going to be 50, and it's going to come back to whatever our source port was that we initialized it on. So for example, if we use port 6783 as our source port going to 50, the response coming back is going to be from 50 going to 6783. So for the reply packet, it would say, oh, the source port is 50 and the destination port is 6783. Just another way if we wanted to play with the ports involved in trying to identify devices that are responding or available, that's another way we can do it. So let's test this one as well. So we have 1, 2, 3, 4, 5. Fantastic. And it's interesting though, for me at least, it says source port is 50. And that's because we're looking here at the reply packets that came back from that device. So 50, 51, 52, 53, 54. There's the time it took for that to come back and the flags involved. So the R is a reset. That device that we sent this to at .38 didn't have services listening and waiting on ports 50 through 54. So it got the TCP send request and it sent back a reset on each one of them, for each one of them, saying, you know what, I don't have any services open on that port, go away. And again, we get some timing information as an indicator of the latency for packets going to and back from that site. If we just want to do a standard type of a ping, we could of course use ping itself, or with Hping, we could actually say I want to ping the entire subnet. We could also specify that we want to go ahead and do it not in order, not start with 1 and then 2, and it can randomize that for us. So this syntax right here, the -1 says I want to use ICMP for this. So Hping, by default, it wants to use TCP. So by specifying a -1, we're saying, nope, just use traditional ICMP. The .x refers to a variable in that last position, so it'll go ahead and it will ping all the possible IP addresses in that subnet. And this option right here, the --ran-dest, that says don't do them in order. Go ahead and maybe pick 5 and then 38 and then 27 and 99 and 250 or whatever, but don't do it in order. The -I says what interface do I want to use, and you can specify the interface you want to use for this actual ping. So we'll go ahead and launch that by pressing enter, and it's going to go through and it's going to ping virtually everybody. Now you can wait for this all to complete, or if it gets the information that you need, you can do a Control-C to go ahead and stop. So I'm going to go ahead and do a Control-C and not wait for the entire range to be done, but you can get an idea, for example, as far as the response time it took to get information back from various devices, and it was not doing them in order. Started with 29, then went to 2, then went to 38, and eventually it would have gotten to every single device. And I guess we should say every single device that responds to ICMP-based request would go ahead and send a reply back. Those that weren't using ICMP or had blocked it or not responding to it. But that, my friend, is why we have the TCP option that we looked at previously, so we can find out about those guys as well. Another option that we can use is to go ahead and make a request of a timestamp from a device. Instead of just an echo request, we can use an ICMP request for a timestamp. And if your device that you're aiming this at responds to that, that's another way of validating that that device is present. So the syntax for that one is right here. The -1 once again represents we're doing ICMP, and this option right here says we're requesting the timestamp, and the -C2 says I only want to send 2. Otherwise, if we leave off that counter, it'll just keep sending them and sending them and sending them. So right here we have 0% packet loss, which is fantastic. We know that device at this address, 192.168.1.1, is there. The reason I point this out is that if this device right there had been configured or didn't allow responses to ICMP echo request, it might allow the response for the timestamp, and that's yet another way we can validate and verify that a device is sitting there. As we give Hping a little workout here, another option is to go ahead and ask for the mask. Now, normally a computer today won't reply to that. Somebody sends an ICMP message with a mask request, and the response back is going to be, nope, I'm not going to tell you what my mask is. You don't need to know that. You just send me packets, and I'll process them. So for this packet right here, that's exactly what this is. I'm doing Hping3-1s for what? ICMP, perfect. This is the destination, and this is the actual information I'm sending. I'm asking for the ICMP address request. The mask request effectively is what that is. And the C2 is the count. How many times am I going to send this? Now, I had 100% packet lost. I got no information back from this, and that's very likely because this device, which happens to be like a Palo Alto firewall, it doesn't respond. It's not willing to give up that information. Another option with Hping is the option to do a scan. Now, by default, it's going to be doing TCP unless we specify that we want ICMP or UDP or something other than TCP. So this -8 right here represents the scan. There's our range. We want to scan ports 50 through 56. And we're going to specify this is our destination. Now, that's a DNS server from Google. And what this is going to tell us is whether or not any of those ports are open on that server. Now, DNS requests are typically UDP, and it's port 53. However, very many DNS servers also have TCP, port 53 also open. So if this is true with this DNS server of Google right now, this should give us a response back with the port that it found open. So we'll press enter, and it launches it and says, you know what, sure enough, it scanned 8888, ports 50 through 56, and it said I found 53 was open. There's the flags involved in the packet that came back, and all the other ports, 51, 50, 52, 54, 55, 56, they all were not responding. There was no open services on TCP on those ports. Now the question is, does DNS really need port 53 for TCP open? And the answer to that is depends on what you're doing with that port and with that service. But what we do know is on this server right now, or at least one of the servers that's responding is 8.8.8.8, and there could be any cast addresses, so they could have hundreds of devices sitting at 8.8.8.8. In any case, we know that this server that we just talked to, it is open on port 53 at this moment. So let's say we have a device, it's not responding to our TCP SYN request, it's not responding to ICMP anything. How can we still test it? And the answer is we could try UDP. Now, UDP is, connectionless. It doesn't do acknowledgments or sequence numbers. However, we can make requests to a specific UDP port. So the fun thing is that if we send a UDP request and that device burps, it does anything, it responds back to us, he's just given himself up. We know that there is an entity there at that IP address because he just gave us some feedback, or something that pretended to be that device gave us some feedback. So to launch that, we would use this Hping, and we're going to use -2. Now, -1 is for ICMP. -2 represents that we want to use UDP. There's our target. Again, I'm targeting internally to my private network. I'm specifying the port I want to send it to, and that's the count. So with that being said, let's go ahead and launch it. And look at this. Oh, that's great news. Look at this. We got a response. And that response was right here. Check that out. So ICMP port unreachable from 192.168.1.6. So now we've looked in this tool alone at 3 different methods for validating a device exists. We could use TCP options, we could use UDP, or we could use ICMP. If we get responses on any one of those methods, that device is validating that it exists. Another tool that we played with, Scapy, had the ability to craft virtually any packet we wanted to, and we have a lot of flexibility with Hping as well. For example, let's say we wanted to send a ping message. By default, this with Hping is going to be TCP based unless we specify ICMP or we specify UDP. In this case, the -F says we're going to go ahead and modify the flag, the fin flag, from a TCP header. The P is the push, and the U is urgent. So we're effectively, they call us a Christmas tree ping because we're lighting up the flags, the F, P, and U, and we're sending this packet to this destination. And we're going to do it only 3 times. Now, if you leave off the count, again, it will just continue doing it over and over again. So how could we actually use something like this? Well, let's say that we are reading a periodical and it announces, hey, if you send this, this, and this to a blah, blah, blah version X machine, it's going to respond with the SAM database, or it's going to respond with information that it shouldn't, or it's going to totally wipe out the protocol stack. It's going to be a good DOS. You could go ahead and leverage that. Now, you could use Scapy to do it, or you could use this tool Hping to do it based on what we're trying to craft. But we're simply adding tools to the tool belt of being able to effectively craft packets and send them out right here from Backtrack or Kali. So let's launch this and see if we get a response. Now the 1.38, I believe, is a Cisco router on my local network. I know I have a Cisco router on my local network, and we could verify that. In fact, let's just do that real quick. Let's go to R1 and do an show IP interface brief. And sure enough, that is indeed his IP address right there. So if we go back to our Raspberry Kali box, we sent 3 packets and we got responses, 3 of them. So again, that's just another mechanism for validating a device there. And if specifying certain flags in a certain order was important based on the vulnerability we're trying to exploit or some other discovery process, again, we can craft them right here with Hping. The initial sequence numbers for a device, if they are predictable, that is a vulnerability. And there's some older operating systems that do have very predictable ISNs. If we wanted to verify the ISN sequencing that a device was using, we could use Hping to do that. So Hping3 using TCP, here's our target, which is 192.168.1.38. And I'm going to go ahead and pause this. So here's the play-by-play. The -Q simply says we want to see the sequence numbers. So we can take a look at the output and we can see if there's a predictable sequence number that's going to use after a period of time. And again, older Windows operating systems like Windows NT and Windows 98 had predictable and sometimes the same initial sequence number that they would begin using. So by looking at the initial sequence numbers they're using, we could identify by comparing those initial sequence numbers to a flaw or an older operating system that used it. And that's also going to give us insight into what operating system is running on this system. As an example, let's compare that host, which was .38, which is a Cisco router. Let's compare that against another system at .21, which I believe is like a Windows XP box. And we'll take a look at the difference in the output. So the initial sequence numbers, you'll notice, are a lot shorter. And if after a period of time they became predictable, that would definitely be some type of a vulnerability that we might be able to leverage with an exploit. I'm going to hit Control-C to stop the sequencing. Another example of how we could use Hping is, let's say, for example, we knew that SSH was open on a network device. Now, how do we determine that? Well, we could scan for it using one of the many tools we've taken a look at in this series, including Hping. And then once we know it's open, or that it's an open port for SSH, we could go ahead and flood it. Now, what does a device do, a network device, if it sees a TCP SYN request? It's going to reply. And then what happens if it sees another one? It's going to reply. So a SYN comes in, SYNACK goes back, and we could do effectively, or try to do, a denial of service attack simply by flooding hundreds or hundreds of thousands of requests coming in. So again, presuming that port 22 is open on this system as a open port listening for SSH sessions, -S represents we have a SYN flag going to be set on the packet being sent. There's our victim, the .1.38, which happens to be, in this case, a Cisco iOS router running SSH. The -A is the address that we're going to source it from. Now, that's not really the address of this Backtrack/Kali system that I'm currently on. However, this would be a spoof source address. So we're going to send in TCP SYN request, and the SYNACKs are going to go back to, this could be a second victim here at this IP address. We're going to go to port 22, and the flood option says, "Dear Mr. Computer, just send those out, those SYN requests, as fast as you possibly can." So let's do this as a little fun. I'm going to launch this, and then I'm going to do Control-C. Just going to run that for 1 moment. So now that the attack is no longer running, let's go over to R1, and I'm going to use the up arrow keys to save me some typing here. Let's do a show control plane host open ports and press enter. And take a look at all these ports that are sitting there waiting, trying to establish all these SSH sessions. So here's the spoof source address, and there's the spoof source port numbers that we used, and he shows them as established sessions. He sent a SYNACK back to that address. It's really not fully established, is it? Because there's only a SYN, a SYNACK. There's no final acknowledgement coming back from the client sitting at 254. but now we've tied up a whole bunch of resources on this device. So let's go back and launch the attack again over on the Raspberry Pi. So let's hit the up arrow key there, launch it, and let it run. And I'm just going to let that run for a few seconds. Now, besides just causing a total consumption of all the available VTY lines on that system that we're connecting to, it's also chewing up a lot of resources. That's why with network foundation protection, we really want to make sure that we're limiting this type of an attack on our network core devices by doing something like rate limiting certain types of traffic so it can't overcome the CPU. Let's go back to R1 while this attack is still running. Show process CPU, and let's do sorted. So show process CPU sorted. This is bad news right here. Over 95% utilization, and that's our 5-second average. Over 1 minute, we're at 50%, and over 5 minutes, we're at 21%. But guess what? If I let this run, the attack just continue based on the current settings, all of these numbers eventually are going to be over 95%. Just based on the sheer amount of TCP SYN requests and processing that this router has to personally handle. It can't just forward a packet using the Ceph table. It has to think about it, respond to every single one of those requests. And again, this would be in the absence of the administrator putting in some safeguards to protect against this type of an attack. So I'm going to hit Q, and I'm going to hit the up arrow key again. Let's take a look at it now. And sure enough, it's climbing. And it'll continue to climb as long as I have that attack running. And effectively, this box is not going to be very efficient as an IP packet forwarder if all the CPU is consumed with handling those TCP SYN requests for SSH. Another fun tool that we can use is traceroute. Now, traceroute's fantastic. The way that Unix does it versus a Windows machine is slightly different. We have, with the PC, it uses the actual ICMP messages, and with UDP and iOS, it actually sends out UDP messages. If we want to do the equivalent of a traceroute inside of Hping, the syntax would be something like this. We're going to do -2, which specifies UDP. Remember, by default, if we don't specify a number, it's TCP based. -1 is ICMP, -2 is UDP. And this says I want to go ahead and start at port 44444. The -T is saying I want to do traceroute, and the -N is saying don't bother doing name resolution. So if we want to get a list of all the hops between us and some destination like CBT Nuggets, we could run effectively a traceroute with this syntax. So it's showing us hop number 1, 2, 3, 4, 5. And I want to share with you something. Not every device in the path is willing to cooperate. So with traceroute, we're using a TTL function. So we set the TTL to 1, and we send out, and then we change the TTL to 2 and 3 and 4. Some devices, like some firewalls, don't mess with the TTL, so they're shown up as invisible. Other devices won't respond. And so this traceroute is simply trying over and over again. So at hop number 9, it responded, but hop number 10 isn't. This is important. If you want to skip hop number 10 and have it increase the TTL one more, simply do a Control-Z and it skips that. See, now it's on 11. Now, hop number 11 also doesn't want to respond to us, and that's okay too. A Control-Z again, that puts us at 12. 12 doesn't want to respond either. So they've got 3 devices in the path that are not responding. Very likely, at least one of those is a firewall that doesn't want to play that game. We'll do Control-Z again, and say hop 13, that's okay, no problem. And then it's now trying hop 14, etc., etc. I'm going to hit Control-C, and most of the other devices in this path are not responding. So here's another cool trick, though. Let's say you want to check out load balancing, and you want to see, I want to see exactly, maybe at hop 13, I want to see whether or not this IP address is still being used. For example, if we did this 10 times and hop 13 was different almost every time, that means either at that hop or somewhere before that, we are doing load balancing. We're going over an alternate path to get to a given destination. Well, with this option, with Hping, we can say, you know what? I just want to see hop 13. So it'll manipulate the TTL so that only that device at that hop will see the TTL is exceeded and send us the replies back saying, hey, the TTL exceeded, I'm killing this packet, here's the response. Because that's how traceroute works by default. We're building this information based on the responses back, the ICMP messages coming back from those devices telling us that they kindly killed or dropped our packet. Now, just to round this out, let's say that the UDP traceroute function wasn't working. Could we use TCP for that? The answer is yes, we could. And to do that, we're going to use the -S, which represents a SYN flag is going to be set in the TCP packet, and we're going to specify, for example, port 53. So the intermediate devices don't really care about the TCP header information because they're not getting that far. All they see is the details regarding the actual TTL at IP, killing the packet when the TTL is exceeded and sending us a response message. So just like before, now that we're using TCP, hop number 10 doesn't want to cooperate, so we could do Control-Z, Control-Z, Control-Z. Hop 13 is cooperating. I'm going to do a Control-C as in cat to stop that. And take a look at this hop right here. It looks like the hop was 216, 182, 224, 63 for hop 13. And down here, hop 13 is 216, 182, 224, 249. So definitely a different device at hop number 13. And so now if we wanted to, we could focus just on that hop to take a look at all the different possibilities we might get back of the devices at hop number 13 who are saying our time to live is expired. So here's our syntax for Hping. The -s represents the SYN flag being set. www.cbtnuggets.com is the domain name. It'll be resolved to an IP address. P80 represents port 80. The -t representing trace route. The -ttl13 simply representing that we're going to set the TTL in this packet to 13. So we're not going to bother setting it to 1 and then setting it to 2 and then 3 and building this entire path. We'll set it to 13. So everybody will go ahead and forward it except for hop number 13, who's going to reach TTL 0, kill the packet, respond back to us. And if there happen to be lots of different devices at hop number 13 based on load balancing and the path that we're going through, it'll show up very, very nicely. This option right here says don't bother changing the TTL with your trace route, just keep it at 13. And the -n says don't bother trying to do name resolution as it was up here. So let's go ahead and launch that. And as it goes out, you'll notice that it's all hop number 13. And I have a whole bunch of different addresses. There are a boatload of paths. So I'm going to do a Control-C to stop that real quick. That way the syntax will still be up here if you want to see it. But check this out. Looks like we have 75 was used a couple times, and 51 was used a couple of times, and I don't see any other duplicates. So either at this hop or somewhere before this hop, we're taking alternate paths for most of our packets that are making their way to www.cbtnuggets.com. One other thing I'd like to share with you in this nugget is the ability to interact with Hping. Now to do that, you're going to type in Hping3, the command, press enter, and that gives you a command line interface into the application. So from here, very similar to the function we had with Scapy, we can craft and carve out the actual syntax of the packet that we want to send. We can also use TCL scripts and get very, very fancy with the features we use within Hping. So in this case, if we were to send this packet, the source address would be 192.168.155. If we wanted to spoof and lie about the source address, we could definitely do it. The destination address would be this. The TTL would be that. We don't have to include those options. These are just, some of the IP header content that we're going to add. For TCP, so this is layer 3 right here. So for layer 4, we can specify the ports we want to have in use. So the source port, the destination port, any flags that we want to send, we press enter. It's going to go ahead and send this packet out on the network. And this is an example of how we could interact with Hping. In this nugget, we've introduced the concept of Hping, another packet manipulation tool that can be used to carve out and create the exact packets that we want to do untraditional like discovery of devices with pings using TCP, UDP, as well as ICMP. I hope this has been informative for you, and I'd like to thank you for viewing.